Hello there, welcome to the third lecture of week 8. So we're going to in this lecture see how mutation testing applies through programs. What I'm going to tell you today is explain in detail the terms that we saw in the last class. Ground string, mutation operator, mutant, killing a mutant. We'll re-understand all these terms but by applying it to a particular program, and then we'll do a couple of examples explaining how to write test cases that will kill the mutants for these programs. So here is an overview of the rest of how the course is going to go for mutation testing. Till now we saw grammars. I didn't introduce you to BNF, but I introduced you to a context-free grammar as it occurs in the syntax of several programming languages. And when I apply grammar-based testing to programming languages, I usually test compilers. Compiler testing is a very involved area. We won't deal with it in the course. No known application of direct grammar-based testing is available for design integration. Grammar-based testing is available for algebraic specifications. Again, because this will involve deep algebraic specification knowledge, I'm going to skip this part of the course. But we will apply grammar-based testing to do input formats like XML towards the end of this module on mutation testing. We'll see this part. We also saw mutation testing in the previous lecture. Mutation testing again applies to all the software artifacts. It applies to programs, source code of programs, where it mutates programs. We'll see that today and in the next lecture. Mutation testing can be applied for design integration. It mutates operators that that tests basically how one module calls another module and all the integration operators that a particular programming language has to offer. Mutation testing can be applied to specifications, especially to finite state machines. There are mutation operators available for model checkers like SMV and new SMV. Because this course is not on model checking, I'll skip this part. But we will see mutation as it's applied to input languages like XML. So what are we going to do? Today's lecture will begin with program-based mutation, continue into the next lecture. After that, I'll tell you program-based mutation but for integration testing, and then we will see how mutation testing compares for producing invalid inputs by applying it to languages like XML. So that's the plan for the rest of the modules on mutation testing. So for program-based mutation, which we are going to begin in this lecture, what do? We basically begin with a given program. Please remember that in mutation testing, the given program that you begin with is called the ground string. Then I apply one or more suitable mutation operators to get a mutant or a mutated program. Typically, it's exactly one mutant that I apply. Remember that mutants must be valid programs that must compile for programs for sure, and mutants are not test cases. We have to write test cases to kill a mutant. What was the definition of killing a mutant that we saw? Killing a mutant means that the behavior of the test case of the original ground string program is different from the behavior for the same test case in the mutated program. Here is a simple example. What is this program do? It could be Java, it could be C, whatever it is. If I've just given a tiny little code segment, doesn't matter which programming language it is. So here is this method called min. It takes two arguments, A and B, which are both integers, and then it computes the minimum of A and B. That's what its job is supposed to do, which is the less amongst A and B. So it initializes a local variable called min value, where it stores the value of the minimum. It says let min value be A to start with. If B happens to be less than A, then you change the min value to be B. Otherwise, let min value continue to be A. Whatever it is, A or B, it returns the min value. Simple enough, right? Suppose we want to test this program using mutation testing. What do we do? So here is the original method given on the left hand side. What I have done is I want to check whether this program correctly computes the minimum value. So I will say, is this code correct? Assigning minimum value to be A and then saying if B is less than A, then you reassign minimum value to be B. Is that correct? What will happen if I use the same code, but instead of assigning minimum value to A, I assign minimum value as B? So that is called one mutation. So I take the same program, which is given on the left hand side, and then I consider the same program and I make one mutation, which is given here. How will you read this as? Delta 1, this triangle or delta 1, read it as one mutation applied to this program on the left, which is the ground string. What is the mutation? Instead of this statement min val a, you remove that statement and replace it with min val b. In other words, assuming that this program came from a grammar, at some point in the grammar, this statement as a string would have got generated, min val a. At the same time, instead of generating a, substitute a with b. So on the right hand side, how do I read this? This is the same copy of the program, which is the ground string on the left hand. So the ground string is on the left hand side, the mutant or the mutated program is on the right hand side. What is the difference between the ground string and the mutant? That's this one statement. The statement min val equal to a is not there, even though I've written it here for the sake of completeness. In the mutated program, it's not there. Instead of that, this statement is there, min val equal to b. So what is the mutation or the change that I have done? I've taken this statement in the ground string, changed this a with b. That's how you read the program on the left hand side. Is that clear? In fact, this is just one change. You could make several other changes. So what I've done here is I've given you examples of 6 different mutants for the same min method. How do I read these 6 different mutants? The one on the left hand side is the ground string or the program that is being tested for mutation testing. I can create 6 different mutants. How do I create 6 different mutants? They are labeled here: delta 1, delta 2, delta 3, delta 4, delta 5 and delta 6. How do these come into picture? Delta 1 means take out this statement min val equal to a, replace it with min val equal to b. All other parts of the program remain the same. What does delta 2 mean? Take out this statement if b less than a. Instead of that, keep this statement if b greater than a. So that gives me a second mutated program from the ground string on the left. Similarly, the third mutated program says take out this if statement b less than a. Instead of that, keep this b less than min val. And what do these mean? These mean that you insert a new statement called bomb instead of min val equal to b. I'll tell you what the statement bomb is. It reads a little funny, but it makes sense. The fifth mutation says instead of min val equal to b, what will happen if you do min val equal to a? That's the fifth mutation. Sixth mutation says instead of doing min val equal to b, you do min val is equal to fail on 0 of b. Fail on 0 is again another special mutation operator for Java. I'll tell you in a minute what it is. The rest of the program is the same. So how do I understand this? The program on the left hand side is called the ground string. From the ground string, I pick one statement at any point in time and I make a change to that statement. On the right hand side, I have shown you put together in one consolidated program how 6 different changed mutated programs look like. The first mutated program takes this statement min val equal to a, replaces a with b. The rest of the program is the same. The second change is you take this statement b less than a, instead change it to b greater than a. That's the second mutation. Third mutation says instead of the statement b less than a, change it to b less than min val. Fourth mutation says instead of min val equal to b, call this method called bomb. Fifth mutation says instead of min val equal to b, call min val equal to a. Sixth mutation says instead of min val equal to b, call min val equal to fail on 0 of b. Please remember, even though I have put it inside one program, what I actually am depicting in this single program are 6 different mutants that you can apply at any point in time, one at a time, to the given ground string program on the left to get 6 different mutated programs. So this one consolidated thing corresponds to 6 different mutations. Please remember that. So this is what I explained to you. Mutants 1, 3 and 5 are basically called variable reference mutants because they replace one variable reference for the other. Let's go back and see. Mutant 1 replaces a with b. Mutant 3 replaces a with min val. Mutant 5 replaces b with a. So it just changes the variable reference. Mutant 2 changes a relational operator. Let's see that. If you go back, mutant 2 changes this less than to greater than. That's what is this mutant 2. Mutation 4, I told you, right? That the bomb statement, which seemed a little funny. That's a special mutation operator. It's called like that because it causes a runtime failure as soon as the statement is reached. You might wonder, what is the point in putting the bomb statement instead of doing this min val equal to b? Typically, there is something called random testing or crash testing a program. Bomb statement is very useful to see how the program behaves when it randomly crashes. So by applying this bomb mutation, by replacing min val equal to b with that bomb statement, I'm checking for random crashes in the program. The sixth mutant is another very special mutant operator, this mutant fail on 0. What it does is that it's a method that causes a failure if its parameter is 0. If the parameter is non-zero, it does nothing. Does nothing meaning what? It just returns the value of the original parameter as it was. So if you go back, this was the sixth mutation. I took this statement min val is equal to b in the ground string, and instead of b, I put fail on 0 of b. So it's like saying what would happen to this program if the value of b was 0. In testing, usually during unit testing and debugging, it's recommended that programmers give every variable's value as 0 and test. So this fail on 0 mutant is very useful for that. It basically takes this ground string program. By changing b to fail on 0b, it checks how the program behaves if the parameter b is 0. If the parameter b is non-zero, it will just replace it with the parameter and behave as if the original program would behave. But it will tell you what happens if the parameter is 0. So it's useful for making a variable 0, which is a recommended practice in testing, and to test a program for that. So how do I create mutants of programs? As I've always told you from the time we began mutation testing, exhaustive list of mutation operators are available for several different programming languages. They can be used for unit testing, like we saw in this example of program. They can also be used for integration testing. In the next lecture, I'll show you exhaustive list of simple mutation operators that can be applied to Java programs and to programs in C. The goal of mutation operator is to mimic simple programmer mistakes. If you see this example, you'll understand the statement, right? Maybe the programmer made a mistake and this is a correct program, the ground string. Maybe instead of writing A, if he had written B, then how would the program behave erroneously? Similarly, instead of less than, suppose the programmer had written greater than, then how would the program behave erroneously? That's what these mutation operators do. They make small changes that will reflect typical mistakes that a programmer will make, and then see how the change makes the program behave differently. Mutation operators, which of these operators to apply? We saw 6 for that example. The choice is up to us. Sometimes we might want to test for some parameters of the program, then you choose mutation operators accordingly. Sometimes you might have audit requirements which say that you test for such requirements, then you might have to apply all the recommended mutations. It completely depends on what is the current status of testing. Test cases have to be effective in the sense that they have to make the mutated program come up with a different output than the original ground string program. And as I told you, testing literature studded with different mutation operators and testing for mutation operators. There are several variants of mutants that one can define. In fact, these terms might be hilarious, but that's how it's lingered on in the mutation testing community. So you say a mutant is still born if the mutants of a program result in invalid programs that cannot even be compiled. As I told you, right, when I mutate a program, I need another program, that is the mutated program, to be valid, syntactically valid, because I need to be able to execute my test case on that. But suppose I mutate in such a way that I get a program that is syntactically invalid and cannot even be compiled, then that mutant is what is called stillborn mutants. We don't really need such mutants. They are not useful for testing. A trivial mutant is a mutant that can be killed by almost any test case. What do we mean by killed by almost any test case? That it's so easy that you don't have to put in much effort to make it different. It's almost easy to apply, and it's not useful for testing how the program behavior changes. An equivalent mutant is mutant that is functionally equivalent, in the sense that you've taken the ground string program, you've made a change to the ground string program, resulted in a mutant, but no matter what you do, you can't find a test case to kill it. In the sense that the ground string program and the mutated program always produce the same output on every possible test case, in which case the mutant is called an equivalent mutant. There's one more kind of mutant which is called a dead mutant. These are mutants that are valid, but they can be killed by almost any test case, right? that can be not by almost any test case, but they can be killed by some test case. These are the real mutants that are needed for our testing. So we saw the notion of killing a mutant. What does it mean? It means that given a program and a test case, I apply mutation to a program, get a mutated program. If the test case is such that the behavior of the original program on the test case is different from the behavior of the mutated program on the test case, then you say that the mutant is killed. It may not be necessary to see the change only by observing the output all the time. If you remember, we saw this reachability, infection, propagation and reveal model, RIPR model, in the first week of this course. All that I want to know is that the program behavior of the ground string is different from the program behavior of the mutated program. I need not wait for the program to reflect that change all the way down the output. Maybe somewhere in between a program, I can do a printf to see if the behavior at that point in the statement is actually different. That's all I'm interested in. It might be too much to expect that the behavior that is changed at that statement that was mutated in the program, it propagates all the way to the output. It might be difficult to do that also. So sometimes I require that it propagates all the way to the output. Sometimes I'm happy that the behavior at that mutated statement is different from the ground string. We have to refine the notion of killing a mutant to understand this. So we make killing the mutant as strongly killing mutants and weakly killing mutants. Strongly killing is what we saw as killing a mutant earlier. Strongly killing mutant means given a mutant for a ground string program P and a test case T is said to strongly kill the mutant if the output of the program is different from the output of the mutated program is different from the output of the ground string program, which means propagation has happened all the way and revealing has also happened. The test case has managed to strongly kill it. So I change mutation coverage to strong mutation coverage, which says for each mutant, test requirement contains exactly one requirement to strongly kill that mutant. A weaker notion of killing a mutant, which is what I explained to you now, is that I might do a mutation by making one mutation operator to a program, but all that I want to know is that at that statement, is there a change in the behavior of the program? I may not expect the change to propagate all the way to the output. That's what weakly killing a mutant captures. So what is weakly killing a mutant? Given a mutant that modifies a particular location L or a statement in the program and a test case T is said to weakly kill the mutant if the state of the program P on applying T is different from the state of the mutated program immediately after that statement L at which mutation was applied. Is that clear? So just as for strong mutation coverage, we take mutation coverage and refine it to weak mutation coverage. What does weak mutation coverage say? For each weak mutant M, TR contains exactly one requirement to weakly kill M. So we'll go back to the min method. So I'll show you the program and the first mutant. So this was the min method. This is the first mutant that I applied. Basically take the statement minval equal to A, change A to B. Okay, now I want to understand, is this mutant can be strongly killed, can be weakly killed, is it a dead mutant? I want to understand what it is. So what do? I go ahead and do my reachability, infection and propagation condition. Reachability means what? I need to be able to reach that statement. If you go back for a minute and see, I can always reach the statement because it is right the second statement. So reachability is true. Propagation means what? Infection means what? That this test should be different because this is the only test based on whether it passes or fails. This statement will be executed, right? If this passes, the result is going to be different. If this condition fails, the result is going to be different. So that's what infection deals with. Reachability is always satisfied as it's in the first statement. Infection means the value of A must be different from B. That's when the if condition will be tested. Propagation means mutated version of minimum must return an incorrect value. That is, the statement in the if block must not be executed. If it must not be executed means what? The condition of the if statement B less than A must be false. So the full test specification for reachability, infection and propagation says you just AND them. Reachability is true, infection is A not equal to B, propagation is B less than A equal to false. If you simplify this logical predicate, true and A not equal to B gives me A not equal to B. B less than A equal to false is the same as B greater than or equal to A. So if I add these two conditions, it means B is not equal to A and B is greater than or equal to A. So the equal to and not equal to cancel out. I just get B greater than A. So what it means that give two values which are inputs to the program A and B such that B is greater than A. Then you'll be able to kill that mutant. So some test case like this, like for example A is equal to 5, B is equal to 7, which satisfies this condition B greater than A, will kill the first mutant. Right? Why? Because the original program will correctly return 5, which is the minimum value. Mutated program will return 7 because I've changed the assignment from B to A and the if condition didn't pass. Is that clear, please? So now let's look at third mutant. We'll go back and see what that third mutant is. So here is the program and here is the third mutant. What does the third mutant do? It changes this if statement. In particular, it changes the predicate in the if statement. It replaces if B less than A, it replaces it with if B is less than min val. That is, instead of doing A directly, it replaces it with B is less than min val. So this is the original program or the ground string. In this program, this statement replaced like this is the mutated program. Let's understand what are reachability, infection and propagation conditions for that mutant. I believe that it will not have bigger change, because if you see just before that in the program, the value min val was assigned to A, right? So min val and the variable A have the same value at that statement in the program when that if statement is executed in the program. So even normally you should understand that replacing one with the other in the if statement should not have any effect. Which means what? Let's look at how does it reflect on the reachability, infection and propagation conditions. So reachability as always is true because I can always reach that statement. What does infection condition mean? Infection condition is that the if should be tested, which means B should be less than A, and the fact that B is less than A should not be the same as B being less than min val, because the mutant replaces A with min val, right? Independently, just from the statement before this, we know that min val is equal to A. We know that min val is equal to A. So what do we mean by that? We know it because the statement holds. If I simplify it, what do I get? I'll get A is not equal to min val from this part, because B is less than A and it's not the same as B is less than being min val. And I also know from this assertion that min val equal to A. If you read this independently, you see that A is not equal to min val and A is equal to min val. This is a contradiction, right? If the fact that this is a contradiction in logic means what? It means that I cannot find any test case value that will do infection and propagation for this condition, which means this is an example of an equivalent mutant. So to understand reachability, infection and propagation well, we'll go through another small example. So here is an example that tests if a given number is Boolean or not. If it is Boolean, it returns true, otherwise it returns false. So Boolean is a method, is even is a method that returns a Boolean value, takes an integer x as argument. It first checks if x is less than 0. If x is less than 0, it makes it a positive number. Then it assigns x to 0 and then it divides it by 2. If it divides it by 2, and every even number should be divisible by 2. That's what this check condition. If it is divisible by 2, then it returns true. Otherwise, it returns false. This program is simple enough to be clear. Let's look at the reachability, infection and propagation for one mutant in the program. What is this mutant? This mutant, instead of keeping this original statement as x is equal to 0 minus x, replaces it with x is equal to 0. So again, what is reachability for this mutant? Reachability means this if condition should be passed. That's how I get to statement number 4. For this if condition to pass, value of x must be less than 0. So that's what is written here. X is less than 0. For it to be infected, x must not be equal to 0. Why? If x is equal to 0, then both 4 and the mutated version of 4 will return the same value. But if x is a number that is not equal to 0 and in fact less than 0, then mutated version of 4 will make it 0, but the non-mutated, the original 4, will not make it 0. So infection is that. So let's consider a test case of the form x is equal to -6, right? So in the original program, the value will be 6. In the mutated program, the value will be 0. But then, if you see, both 6 and 0 are even numbers, which means both of them will become divisible by 2 at line number 5, in which case the program will return true for both versions. I want the program to return false value for one version. How do I do that? I have to give an odd negative integer. If I give an odd negative integer, then here there will be infection, and propagation will also happen, because the condition in line number 5 will return 0 as even number because of the mutated version of the program, whereas in the original version it will still be an odd positive number which is not divisible by 2, so it will return it as false. So for reachability, infection and propagation, which results in strong killing of mutants, I want the test case to be an odd negative integer. So here is a summary slide that explains the process of mutation testing. I begin with a program P, my ground string, which is my input program to be tested by using mutation. I create one or more mutants for the program. How do I create mutants? I have a standard list of mutation operators, which I will be telling you in the next module. Using one or more of those mutation operators, I create different mutants. Please remember that per one mutant, I have to use only one mutation operator. It is not recommended that you use more than one mutation operator. Now, if the mutant turns out to be equivalent to the original program, then there's no point in trying to test it. So usually there are these things called equivalence checkers, which return yes or no for a large number of cases, which basically tell you if the mutated program is the same as the original program. If it is, then there is no point. If it is not, then I generate test cases and I run the test cases on the program first, then I run the test cases on the mutated program. Because they are not equivalent, the outputs should be different. If the outputs are not different because propagation is not achieved, then the test case is called ineffective. I eliminate it. And I will usually have a threshold that is defined independently by, let's say, a quality auditor or somebody, which tells you how many mutants to test the program for. If I've reached my threshold, then I finish, exit. If there are any errors that I found, then I fix the program and I go back. If I have not reached my threshold, then I generate more test cases and repeat this process. So this is how broad level mutations testing works step by step. So here's a summary of mutation testing for source code. It's one of the most powerful forms of testing source code. In later this week, I'll tell you how mutation operators and mutation testing subsume several other coverage criteria that we have seen. It's very powerful for both unit testing and for integration testing. And the biggest problem is we need to pick up an effective set of mutants that will give us an effective set of test cases, such that if the original program P has an error, using mutants we will be able to identify the error. What I'll do in the next lecture is I'll tell you about typical mutation operators that you can use for programming languages like C or Java, and that will help you to define mutated programs from ground strings. Thank you.